We are generating massive data sets and training dense machine learning models at a pace that is outstripping the thermal limits and processing timelines of our most powerful supercomputers. The limit is built into the hardware itself. Classical computing relies on physical transistors to represent data in a strict binary system. Every piece of information must be encoded as either a 0 or a 1. Because of that binary structure, classical systems process information sequentially. They execute instructions one step at a time, calculating the first path, then the next, and then the next. This creates what researchers call the curse of dimensionality. When you try to simulate highly complex interacting systems, like the precise molecular interactions required to design a new pharmaceutical drug, the number of possible variables explodes. This chart compares a standard linear processing timeline against an exponentially expanding problem space. Because a classical computer processes data sequentially, it scales poorly. It checks every possible molecular combination one by one, driving the required time and energy to impossible levels. Computing a high-dimensional simulation on traditional hardware would take millions of years to complete. We haven't run out of ideas for new materials or medicines. We have run out of time. That sequential bottleneck prevents classical architecture from solving high-dimensional problems within a human lifespan. Decades ago, physicist Richard Feynman noted that nature doesn't operate in binary. To accurately simulate the physics of the real world, you need a machine that operates on the rules of quantum mechanics. That requires a new basic building block of information, the quantum bit, or qubit. It abandons the rigid constraints of the classical bit. This is a block sphere, a visual representation of a qubit. Instead of being locked to the top or bottom poles as a strict 0 or 1, the qubit uses a property called superposition. It exists as a combination of multiple states simultaneously, occupying the space in between. When you link these qubits together, they utilize entanglement. They share interdependent states, meaning an action on one instantly affects the other. As you entangle more qubits, the computational space stops growing linearly, it scales exponentially. By combining superposition and entanglement, a quantum system can process computational operations across vast solution spaces in parallel. Instead of checking a single path, hitting a dead end, and starting over, quantum mechanics allows the computer to explore the entire maze simultaneously. But harnessing that parallel power comes with a massive catch: quantum state decoherence. Qubits are incredibly sensitive. To maintain superposition, they must be isolated in deep vacuums and cooled to temperatures hovering just above absolute zero. The slightest environmental disturbance, a tiny vibration, a stray magnetic field, or a microscopic fluctuation in heat, creates noise. That noise interacts with the qubit and instantly destroys its quantum properties. The timeline for this degradation is brutal. In current hardware, total decoherence happens in less than 300 microseconds. The moment decoherence hits, the quantum system loses its memory. It collapses back into a rigid classical state before it can finish calculating the math. The primary challenge in scaling these systems shifted years ago from theoretical mathematics to the engineering required to keep a fragile state stable. Because of that extreme fragility, the industry is currently operating in what is known as the noisy intermediate scale quantum, or NISQ era. Since decoherence prevents us from building fully fault-tolerant quantum computers today, we aren't throwing away our traditional server racks or laptops anytime soon. The immediate, real-world workaround is hybrid quantum machine learning. This cyclical workflow schematic shows how the division of labor actually works. A classical server still does the heavy lifting. It stores the massive bulk data and runs the standard repetitive optimization loops. The classical system isolates the single, most complex mathematical bottleneck and routes it to the quantum processing unit. The QPU acts purely as a rapid accelerator. It receives the task, calculates the parallel states in a flash, and fires the optimized result back to the classical server in the fraction of a second before decoherence hits. Researchers are actively using this exact synergistic loop right now to tackle dense, high-dimensional problems in advanced molecular modeling and cryptography. The future of computation relies on a partnership. Quantum architecture will work alongside traditional computers to calculate specific patterns in nature that remain invisible to classical systems.